Am I here? Hello, hello. Good. Can you hear me? Yes, yes. Good afternoon, or good morning. I don't even know. Is it? Yeah, it's good afternoon. It's actually super nice weather today here in Boston. I don't know where you guys are connecting in from, but if you want to say hi on the chat, I like to see. I like reading where people are calling from. I see familiar people, familiar faces. D-Bag, Kartik, Sujai, Saeed. How are you doing? Uh, I'm so tired today. Oh my god, I don't know what's going on. Ay, how are you guys doing with all this crazy time, quarantines, viruses, Zoom calls, work? Hi Albert from Dubai. How are you doing? Uh, I I don't know. I mean, honestly, my life hasn't changed that much. I don't know if that's a good thing or a bad thing, but I still spend tons of time in front of my computer. Um, I guess the good thing was that one of the good things was that this whole situation was kind of like a push in the back to like, okay, you've been meaning to do this, to make this channel and do these live streams for a long time, so why don't you just do it, you know? So, and hence we're here, you know? Oh, from Istanbul. I was there. When was that? I was there in the summer of 2011. I was teaching a parametric design workshop. So I was actually teaching a parametric camp workshop. That was the origin of parametric camp, actually. Uh, I had such an amazing time. Istanbul is so beautiful. People were so welcoming and so nice. A friend of mine, Erdem, he took me. We rented a fisherman boat and we started just like going up the Bosphorus, and we saw some dolphins. It was just so cool. Everything was so nice. I had an amazing time. Uh, Hi Baba, how you doing? Hi. Okay. So, what are we doing this afternoon? My plan was to start the introduction to Grasshopper playlist series, but I don't think I'm gonna do that because I don't feel ready for the challenge. I feel like I want to do like a third video talking about mimics, and I want to show you guys how to take how to go and take ShaderToy shaders and use them in mimics, and maybe adapt them and change them a little bit to the whole idea of like, oh, it's a webcam stream and there's like some person on the front. So I think I want to do that a little bit. Hey Salvador, how you doing? And and if we have time and my brain allows me to, I may do the algorithmic modeling challenge that I was going to do, the Calatrava, one of the Calatrava buildings. That one shouldn't take much time. It's not very difficult, and I want to have it as like a simpler beginner level Grasshopper tutorial. So we may do that, and I may just open it up to Q&A by the end of the stream. So how does that sound for a plan? Huh? I Okay. So where are we? Um, yeah. So I think we can probably start. Oh, also a few reminders. If you were not here this morning, we are going to move permanently to this channel. So I guess if you're here, you're in the right place because this is where the future lies. If you're following me on my personal YouTube channel, that's fine too. But in the future, we're only going to be streaming here. So if you subscribe your notifications to this channel, that's where you want to be. And I also shared this morning, we started a Discord channel. That was actually Kartik, who somewhere is here in the chat somewhere. He was the one who volunteered to take this. So I'm going to paste here the link, the invitation to the Discord channel. So if you want to join, It's going to be a place where we can all have conversations and introduce each other and know each other a little bit better and have more like an offline conversation aside from the chat on the live streams. Okay, so I explained a little bit about the Discord in the video this morning. So if you want to check it out, just go to the previous video and you can take a look at that. If you join, please come over here to the introductions channel, and we have a template. We have a small template with emojis, which is kind of cute. So so you can like introduce your name, where you're from, how do you heard from us, what kind of things do you like, etc., etc. Okay. I like coding, but I also like humans, so I like to know who am I talking to and who I want to hear about your lives as well a little bit. Okay, so let me get my brain together. So we're going to record a quick video where I'm going to show how to go to ShaderToy, how to find a proper shader that we can adapt to mimics, and then perhaps like tweak a little bit of the parameters. Okay, so for that I'm going to open a Chrome window and I'm going to open ShaderToy, and then and then I'm going to explain. I'm going to record the introduction at the end. I'm going to explain how to find shader toys that are good for mimics, and then I'm going to show a bunch of examples. Okay, so let's do that. I'm gonna put my decaf coffee somewhere here. I'm gonna make myself some room, and let's get to this. Okay, all right. Obviously, the first thing that you want to do is you want to come to the website ShaderToy. You probably want to sign up for an account. I'm already logged in here. And then we're going to browse. We're going to look for shaders that are cool and that we want to bring in as backgrounds or as the image that we're projecting in our video meeting calls. And because there's like a lot of really cool stuff on ShaderToy. Like for example, I really like this one. I was explaining in the previous video how that we're seeing here is entirely generated procedurally with mathematical formulas and equations. There's no geometry, no meshes, no lighting, no nothing. Everything is just computed numerically, which is amazing. It's one of the powers of ShaderToy, and you can see how fluid and how fast it is, right? So, but since what we're looking for here is shaders that are specifically designed to be maybe more like backgrounds to our image, or that play with the texture of the image, of the video, of the webcam that we're fitting in, we need to find like some that are a bit more specific to that end. Okay, so for example, what I'm going to do is I'm going to go to browse, and you can see that I get a lot of like a lot of really cool things that are really cool shader toys that are trending and that are hot right now. It takes some time because it's now rendering a lot of really heavy lot of really heavy shaders. So you can see that my computer is a little laggy right now, but I'm going to click here on webcam. And I'm going to click on webcam because this is a filter that is giving me the shaders that are specifically designed to take an image and to process that image and turn it into like a filter version of itself, right? So I'm actually going to show this one. I'm going to show this one too, but I think I want to go to where was the one that I saw before. There is one that is called edge detection that I really liked a lot. I think it might be here. Well, if anything, I have a link here. So I'm got this one here, edge detection. Okay, so I'm going to click here, and my computer is running 17 different things at the same time. So, but you can see, right now, what you're seeing is that Chrome is taking the webcam feed of a webcam that I have here sitting in front of on my desk, and you can see that what it's doing is running an algorithm that is doing edge detection. So you can see on my image how there's like, is this ghost version of myself? Ooh, ooh. Oh, and the teeth look really scary, huh? But this is done, actually this is not very complicated technique. This uses a 3x3 matrix called like an image kernel to do edge detection. That's probably something I want to talk about at some point in another tutorial. But what we're going to do is we're going to take this code and we're going to try to port it to ShaderToy. Okay, so that we Mimics, so that we can use this filter in our video conference calls. So what I'm going to do is I'm going to take all of this and I'm going to copy paste it into a new file here. Okay, and I'm going to give this a ShaderLab type so that I can get a bit more of better syntax highlighting. What's good about this and why I chose this filter is because, as you can see here, it has an I channel 0 that is taking the webcam feed, which is exactly how the shaders in Memex work. So this is going to be a really good fit for porting to Memex. It also doesn't have any buffers, which is probably something you want to take a look at, because that makes things much easier. So I'm going to close this and I'm going to open a new Zoom meeting, and I'm going to set things up so that we can try things out. Okay? Hey, Hari Prasad, Ramthin, how are you doing? Okay, so I'm going to start a Zoom call, and my Zoom call. Here and here. And this is, okay, here. All right. Where are we here? Okay, yes. There's so many of me everywhere. Whoa. Hi. All right. That's such a good fall. Here. Okay. All right. Let's get back to it. Great. You can see I did a little bit of setup. So now what I have here, all the way up here, is I have a Zoom meeting running right now that is taking my Memex camera as an input. And I have the Memex UI here running a custom shader. And here I have the file with the custom shader that I did in the previous video, where we took the chroma, we cropped the chroma out, and then on the background of the chroma, we just created this this black to white gradient. Okay, if you want to learn how I did this, you should definitely check my previous video on how to do custom shaders. Okay, but this is the main file that has this. Here is the main file that has the shader that I programmed in the previous video. So what I'm going to do is I'm just going to delete everything. Okay, I'm going to zoom in a little bit, and then here I'm just going to right away I'm just going to go ahead and copy paste everything. Okay, and if I hit save, you can see that it's working already, and that now my custom filter is just doing edge detection. Okay, this worked, copy pasting it right away, again because Memex uses ShaderToy flavored shader language, which means that all the conventions and all the names and all the uniforms have the same names. So in this case, copy pasting just worked right away. Okay. The only thing is that I'm having particular problems because I think my webcam, for some reason, is giving me a feed when it comes to Zoom that is flipped for some reason. So what I would like to do here is I would like to just try to flip the Y direction, and I can very simply do that, I think, by taking the Y coordinate of the fragment coordinates, so taking the Y coordinate and then flipping it. So saying this is going to be to the height of this image minus the value of the Y coordinate itself. And if I do this, yes, so it's flipped. So here you have, for example, here you have now an example of an edge detection shader that you can use in Memix. Okay. Yes, I'm going to copy paste the link here, and then I'm going to show you I'm going to show you how to do this with a different shader. Okay. Let me, before I forget, here I'm going to add the comments here. And I'm going to copy this to my desktop so that I don't forget. Edge detection. Okay. And then here on shaders. Okay. I'm going to minimize this. I'm just going to stop this because otherwise it's going to be very difficult to How cool is this one, huh? Okay. Okay, and this is and I'm going to take this from here, and this is going to be this one here. Okay. I know, right, Said? How cool is ShaderToy? Huh? Okay, let's do more. All right, the next one we're going to try is this really cool Raymarch CRT. I don't even know where to look anymore. I'm looking there, I'm looking there, I'm looking there. TV, old TV, I'm talking from the past. Ooh. I think CRT stands for cathode ray something. I don't know, but this is a really cool shader done by Dean Decoder. So very easy. What we're gonna do here is I'm just gonna and also again rule of thumb: if the shader has one channel, the I channel 0, and it doesn't have any buffers or anything, it is just one page, this is probably like a really good candidate for bringing it to Memix. Okay, so what I did was I've copy pasted the code here, and I'm going to start a new Zoom call, and then this Zoom call is going to use my Memix, and it's using my other camera here. And where is my Memix? Okay, this is the UI here, and it still has the shader that we used before. Okay, so again, for this one, it's literally going to be as easy as copying the code, and then in our main shader.txt file, just deleting everything and pasting this. And as I hit save, you can see that Now I have my CRTV filter on zoom. This is very zoomable, right? This is quite zoomable here. And I think I also want to flip the my y coordinates. So at the very beginning of main image, I'm going to say this is equal to I resolution x divided by frag coordinate dot y, and this should work. Oh, minus, yes, minus, and I flip it again. Okay, so okay. All right. And let's try another one, right? Okay. I'm going to copy paste this one, shader, CRT, CRT. And shader lab, and then here, I don't need this anymore. Okay, and I'm gonna end this call. And the last one that I'm going to do is going to be this one. Two. Okay, but this one I'm going to tune it a little bit more, because I'm going to take it and I'm going to put all this like flicky. I'm going to put it in the back of my image. I'm going to take the chroma and I'm going to do some chroma magic here. And I think this one is already inverting the so this is going to work right away off the bat. Here, there. And last but not least, we're going to try this one here. It has a very strange name that I can't read in Chinese, but it's created by FMS Cat. It's quite simple. It's just this like bang effect of like rays coming in. But I like this one because what we're going to do is we're going to copy paste it, but then we're not going to leave it there. We're going to take the advantage. We're going to mix it with the shader that I did in the previous video where we cut out the chroma. And what I'm going to do is I'm going to use the chroma to cut myself out and then have this thing bang in the back of my body, so that you see these rays here that are in front of my chest and the ones on my head, in the back of my head, so that everything is on the back. Okay, so let me copy this and bring it to Visual Studio. I'll see you in a second. Okay, so I'm going to copy paste this. I'm going to shader lab. Okay, and then here. And then here. Okay. And here we are. We are back on the main shader file that has the CRT one that we just copy pasted. I'm going to delete everything and I'm going to paste. Remember the example that I did where I had the chroma and I had a gradient in the back? So I'm going to copy paste all of that here. And you see, we're back where we started. Okay. And I'm going to also at the same time, I'm going to take all of this. This is the code for the bangy bangy shader, and I'm gonna paste it all the way at the end. Okay. As I do that, this is not going to work because I do have two functions on the same shader that are called main image, and only one can exist because this is the one that the shader will call, and then that will execute the main shader process. So what I'm going to do is I'm going to take everything that is not main image. I'm going to take everything from the second shader, the one that I just brought in. I'm going to take everything that is not main image, that is just helper functions, and I'm going to copy it at the beginning. And especially the defines, I'm also going to put in all the way at the very beginning so that they're available everywhere on the shader. But I'm going to keep the chroma key function that I had from my original shader, from this one that you are seeing right now. And if I comment out the main image function that was doing the chroma effect, then if I save this, I probably already have this bangy bangy shader, okay? So now what we need to do is we need to find a way to combine them both. So what I'm going to do is I'm going to do the opposite. I'm going to turn on the main function, the one that did the chroma effect, and I'm going to turn this one off. Okay, so this is going to be here. But then what I'm going to do is I'm going to replace the code. So because I want to keep my cutout, I want to keep it in the front. But then in the back, where the gradient is drawing right now, what I want is, instead of that gradient, I want to have the bangy bangy effect here. So what I'm going to do is I'm going to go to where in my main image, where the code that is deciding whether if I draw the gradient or not. This is dead code. I'm going to remove this. But if you see here, remember that when we did the chroma, we received a value k that was telling us how, between 0 and 1, how much chroma, how much correction had to be done on this pixel. So if this was 0, it meant that it was not a green pixel. If it was 1, it meant that it was a fully green pixel. And anywhere in between, it was like a blending transition. So here, what I specified was if the value of k was greater than this slider here, then instead of using the pixel color of the texture, so instead of using the webcam, just use this v value that is 0 at the top of the image and 1 all the way at the bottom, and it gradients. Okay, so what I'm going to do is, instead of this, here is what I want to replace with the explosion effect. So only the pixels that are to be substituted with chroma should get this explosion effect. Okay, so what I'm going to do here is I'm going to take the main code, I'm going to copy paste it here, and I'm going to give it some form. Okay, and then I'm going to save this, and it's not working exactly well. Let's see what is going on. So if k is greater than parameter, then fragment color this one. Otherwise, if that's not the case, then use the fragment color here. Okay, exactly. So what I was doing was, because I had this all the way here, it didn't matter what I was doing because any changes that I was doing here and the assignment to the fragment color was anyway being overwritten by this at the very end. So what I want is, if the value of the chroma is higher than the slider, then fragment color should be all this computation. Otherwise, if it's not, then just keep fragment color like it was, which is with the pixel color. Okay, so this is what I want here. All right, that's great, except for the fact that I'm still seeing the green screen in my back, which is not nice. I probably want to remove that, but at least the explosion effect, now it's behind me. It's not anymore in front of me, which I like. So something that I'm going to do is I'm going to say, well, I think somewhere here, you see here, I am still taking the texture of the back. So I don't think I want to take the texture of the back. I don't want to take the chroma again. what I want to do is I want to mix this color, and I want to say, instead of mixing the final color that is going to come out for the pixels that are with the chroma, instead of mixing it with the texture, why don't you mix it with a black color? So a vector 3 that only has the value 0. And as I do that, then all the other pixels get corrected. I can also change that here for the white value. This is the color of the spikes that are being exploded. So probably I want to do, let's say I'm going to do full red. Okay. So now it's like red. And or I don't know, or purple, why not? Or magenta. This is magenta. Okay. And I'm probably doing some redundant calculations here, but it doesn't matter. This was just more for the sake of illustration. Okay. So with this, I'm going to stop here. Nevertheless, I want to remind everybody who's watching, everybody who might be watching this video, that that the terms of use of ShaderToy mean that all the shaders that are available on ShaderToy have the Creative Commons attribution, share alike, and non-commercial. Okay, which means that I believe this means that you're welcome to take this code and use it for personal purposes, not for commercial ones, so long as you attribute who the author of the code of the shader is, and that if you share it, with the same license. Okay, so be mindful about the creators who put their work out there in the platform, and then just not take it and use it in any terms. Okay, remember that you have to. It's only fair to abide by the terms of the environment that you're borrowing all this knowledge from. Okay. Okay. Well, I hope you have a lot of fun and you create really cool shaders for your video conference, and that you have a lot of fun. Thank you. Okay. All right. So that was there, and then source, and then here okay, and I'm going to save this here as shader bang. Okay, shader chroma. This we don't need. Okay, and with that, I think I'm done with ShaderToy and Mimics today. I think that's more than enough for as an introduction. I'm going to let me change a couple things here before we move on, because otherwise I'm going to forget. And this is the original. Okay. 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 All right. How was that? How did you guys like this? Ooh, I'm really tired today. Oh, it's 2:30 already? Oh, 2:30. Said, can we create loops or physical animations in ShaderToy like in Nature of Code? You can. So for loops, you can do for loops. That's totally cool. Animations, as in like things floating and stuff, it is possible, but since you do not have um, since you do not have a global memory state, so you cannot have like an array of flocking objects, and you cannot read that with each one of the shader in each one of the fragments, then it takes a little bit of a different logic to make this happen. It is possible, but it's a little different. It's not exactly how it would be done with the nature of code. So we might be able to take a look at that in the future, but honestly, I'm not sure when we will be able to get there. Luigi, how do you set up shader for your streaming? We saw that on this morning's live stream, so you can check the other live stream, or you can check the edited videos. I want to edit the videos as soon as possible and post them perhaps over the weekend, so you can take a look at that this afternoon. Hey Andres, how are you doing? Okay, so what are we going to do now? What I have in my list here? I wanted to do an algorithmic modeling challenge. So I'm a little tired, so I may want to go for something a bit easier. Uh, so I had in my mind to do a Calatrava building, one that is in Valencia. It's like a canopy. It's a very nice canopy. So we may just do that, and we might just do it in vanilla Grasshopper, and if we have time, maybe we can do the second part in C#. Maybe not. I don't know. It's also super nice out there. I kind of want to go out for a walk or something. It's okay. That's it. I'm here. I'm here with you. Let me go. I'm gonna go get some water. I'll be right back. Okay. All right. Oh, I didn't record the introduction. Yeah, I did not record the introduction to the previous video. Okay. Okay, so I guess I'm going to do that. Um, mm, 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 mm. Okay. All right, you're here. Yes. Okay. Hi, and welcome to this third part of the Memics video tutorial series, where I'm going to show you how to go to ShaderToy and how to find a shader that is ready to be ported to Memex, and then how to take the code, bring it into Memex, save it as a custom shader, and then be able to now jump on a Zoom call where you have this like cool filter that you can surprise people with, and that you can be a little funky and honestly and honestly be a little more fun than all these like crazy boring Zoom life that we're all going through these kind of days. So yeah, I don't even know what I'm saying anymore. Anyway, yeah, shader toys to Memex. Let's take a look at how to do that. Okay. All right. And oh, okay. So that was it. Oh, woohoo! Okay. I see some new people on the chat and on the video. Um, if you guys haven't subscribed, please subscribe to get notifications when we move permanently to this channel. And also, if you haven't seen it, we have a new Discord, so you can join and have the conversation going on for the rest of the week. Okay. Whew. So okay, let's get started, because the sooner we start, the fresher we are. Okay, so I'm going to open Grasshopper. Yep. I'm going to open Rhino. I'm going to open Grasshopper. And I'm going to take a look at so this is going to be here, so here, and then I'm going to take a look at the actual building. Okay. Okay, this looks good to me. Okay, so this is what we're going to do. We're going to model this thing. First, we're going to do it in regular vanilla Grasshopper, and if we have time, we'll do it in C#. Otherwise, we'll do that at some point in the future. And for this, I'm going to need Grasshopper and Rhino, and probably I want to do some sketching. So I'm going to start some sketching here. Up. And I'm going to lose my pen. It's very hot. I'm going to open the window or something. Oh. There you go. Okay, are you guys ready for this? Have you been to Valencia? Valencia is super nice. I lived there for 2 months, 1 month. I forget. I had a great time. It's a wonderful city. It's like perfect size. It has like entertainment. It has culture. It has a lot of open air space and parks. It's very nice. It has the sea. The food is amazing too. Anyway, am I gonna start with this? Do I like these images? This one is cool. Huh. Okay, I like this one. And I like this one too. Okay, so as usual, I will do the introduction at the end. Um, and then I'm going to, and then here I'm going to explain I'm going to explain the shape of the building, and then I'm going to go into whiteboard, and then I'll just go and start doing this in Grasshopper. Okay. All right. Well, to start with, we can probably take a look at the shape of the building, which is a pretty good thing to do at the start if you wanna, whenever you wanna start modeling some shape. And we can see that in general, the building is composed. It's basically a canopy. It has like some structural shape. This curve, I believe, is probably very close to a catenary curve because since it's only holding its own weight, then it probably makes sense to approximate that to a catenary shape. You can see that the full thing is basically modules. So if we consider this whole thing one span, one module, we can see that each module has two of these catenary arches. And then in the middle, it has one where the beginning, the ends of the curve do not reach the ground, and where the top of this curve is a bit higher than the average. We can probably see this if we find a better frontal image here. Yes, so you can see that the arches that are in the middle of each span reach a little higher, or you can see that here as well. And yeah, and it's very clear to see here on this image as well. So what we're going to do is, in this exercise, we're going to model those arches. We're going to model each span. We're going to model the arch in the middle. We're going to model all these ribs. We're going to model all these ribs that are joining the span, and we're going to model the profile of this beam as well. And something that is interesting is that the profile of this beam has a height, has a shape, has a depth here that is larger than the depth here. So as the beam goes up, it becomes thinner and thinner, which I guess makes sense because it's probably structurally it has less stresses here on the top than in the bottom. So that's something that we also want to model in our exercise. So how about we go to the whiteboard and do some sketching about what are the parameters that we want to control here, and then we go and we start implementing this. Okay. So let's go to sketching, and as usual I'm gonna make a terrible job here, but okay, so what am I going to do? I'm going to do pencil here for this, and then for this here, and then I'm going to do this one here. I'm going to do this one here, and then I'm going to do this one here. Oh, how does that look? I've done worse, right? Okay, and then we're gonna have the ribs here, sort of, and then the ribs here. Okay, and then it's gonna draw in gray, thicker gray, here, 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 here. Okay, and so I think I want to do this this point, and this point, and this point. No, not this one. Okay, now actually I'm going to do this in a new layer. Let me save this. Yes, I'm going to do that in a new layer. So there's going to be this point here, this point here, this point here, this point here. This point here are important, I think. This one, and this one. And then I probably want to do this. I probably want to, I'm going to do pen for this one, pencil. I'm going to control this one. I probably want to control also this height here. This height here. I want to control how many of these elements are in the Y direction. And I want to control how many of these things are in... and I think I'm going to do... so I think I'm going to... yeah, where is X? Okay, so this is going to be X. This is going to be Y. And this is going to be Z. Huh, I'm getting a little better at this game, huh? Okay, so this is going to be, we're going to call this the width, we're going to call this the height, okay, and this is going to be the distance, depth, and this is going to be lowercase h. And what about the point on the top? What about the point on the top? I'm just probably going to make that okay. I'm going to also, this is going to be it's going to be a value, this is going to be h1, and this one is going to be h2. For example, and then we will also want to control the number of these things in this direction, and the number of spans, and also a number, and here I want to control also the number of ribs. Okay, I like this. Oh, and there's something that I want to control as well. Here the ribs are not going to start, the ribs are not going to start right away at the beginning of the curve. They start a little higher. So I'm going to call this the offset of the offset of where the ribs start. Okay, we'll get to that whenever we have to. Okay, so now let me do the recording. Okay, folks, I saved you the hassle of the 15 minutes that it took me to draw this really terrible sketch. But I would like to remind you that this is extremely good practice. You should always draw a sketch and think about what the variables and what is that you want to control whenever you model something parametrically, because it will help you very much in the process. Okay, so what you're seeing here, what you're seeing here is that I have a model, the basic structure of the building is called the umbraco. I don't know how to pronounce that. That's Valencian. And what you can see is that basically we're going to do a modular approach where we're going to have one span, which is what I have drawn here. And the span is going to be two curves that are going to have a width and a height that are going to be controlled by 3 points. And then it's going to have another curve in the middle, which is also going to be driven by 3 points. But those 3 points are going to be elevated from the ground on the base by the factor of h1. And the point on the top is going to be a little higher than the point on the neighbor curves, a little higher by a value of h2. Okay. Once also the width of the span in that direction is going to be called d, as in depth. And at the same time, we will also want to control how many spans of this module we are replicating in the x direction. You see the coordinate system that I drew down there. I can't up. I can't down there exactly. So we want to control how many of these, and we want to control how many ribs. So how many of these partitions are going to be present in the in each one of the modules. Because at the end of the day, what this is about is we want to do algorithmic modeling. We want to model something that is entirely controlled by parameters as much as possible. So that's why instead of assigning numbers, we assign variables or parameters, so that when we are done, we can change those numbers and then we can adapt the shape of the building, and we can decide what is the final shape that we want to get. Okay, that is the beauty of parametric modeling. So let's get started. Okay, so let's do it. So I'm not going to bother. I'm going to start dropping sliders here. So okay. So this is going to be the width. Oh, I'm going to place some bifocals, because you know those people who like text on their components. So and then H, and then I'm going to do what else am I going to do? I'm going to do H1, and I'm going to do H2, and what else? Oh, D. We need D. We need B here, and so this is for the second curve. Okay, and then offset and the number of ribs and number of spans. We can probably look at that later. I don't know. Well, we can do it now. So number of spans, and then number of ribs. I think we will need this earlier before the other one. Okay, let's keep it clean and tidy. Okay. Andres was asking whether if the curves are catenary or not. Oh, you were not seeing what I was doing. Sorry. Andres was asking whether if the curves were catenaries or not. I'm not entirely sure, but I feel they're probably close to catenaries. The only thing is that we're not going to do catenaries in this tutorial, because catenaries are not, Rhino Common does not have a catenary implementation. So we would have to manually do the catenary shape in C#, and that's a little too tedious for my taste, at least right now. So it would take me like at least a full geometry jam to explain that, which I don't feel like doing right now. So maybe we can do that in the future. But because I want to do a C# version of this algorithmic modeling, I'm just going to use a regular NURBS curve for that. Okay. Okay, so I'm gonna start here, and I'm gonna start creating. I'm gonna start plugging in stuff. And I'm gonna start from my point here as well. I like having like an anchor point of sorts. Yes, like the origin point, sort of. Yeah, I like that a lot actually. So because it makes things a bit more parametric even. Okay, let's get going. Wonderful. So what I've done is I've spent a little bit of time preparing my definition and coming from all those parameters that I have defined in my sketch. I have mirrored those with grasshopper sliders. So I have the width, the height, the depth. I have h1, h2, number of reads, etc., etc. And the only thing that I have added is that I have created a physical point here in Rhino that I have brought as a parameter in Grasshopper, because what I would like to do is I would like to able to, once I have finished making this whole thing, I would like to be able to change the point where this thing starts and basically be able to place this building anywhere on my window, on my Rhino window. That would be really cool. So that's why I'm going to start with this point, which is going to be my starting, basically the origin of the building, and I'm going to base the location of all the other points as a reference to this one. Okay. So what are the first thing that I'm going to do? I'm going to create the 3 points that define the first arch. Okay, and that's going to be super easy, because what I'm going to do is I'm going to say, well, the first point on the other end, I need to basically take this point and move it by a distance of w in the y direction. So I'm going to create a y vector with the length of w, and then I'm going to move this point by this vector. Okay, that is going to give me a point that is going to be the second point. Is going to be the other end of this point. And now something that I can do is I need to find the point that is right here, and that point is going to be in regard to this one is going to be a distance of half width in the y direction and a full h in the z direction. So I can probably create a vector from x, y, z coordinates. X is going to be 0, y is going to be w divided by 2. So division. I actually don't like doing. You will see this. I actually don't like doing algebra with regular components. I like expression components a lot, because I see them. I can see the expression, and I can. This is perhaps for dividing by 2 is very simple, but when it's a bit more complex, it kind of makes sense, I think. And then height is going to be this, and then I can take and I can move all of this, and I can copy paste this, and I can move the origin point by this new vector. Okay, and if I take a copy, I like doing this a lot too. If I take a copy of this point here, right, and I place it here, so I have those 3 points here, and what I can do now is I can just draw a simple interpolated curve between the first point, the one in the base, the second point, which is the one on the top here, and then the third point, which is the one on the other end, giving me this curve, this shape, which is a NURBS curve. One thing that I would like to say about this is that I believe in the original building, this shape is probably closer to a catenary. I believe, I'm not entirely sure. And Grasshopper does have catenary implementations, so you can use a catenary curve. The only thing is that the catenary curve in Grasshopper is controlled by the 2 base points, but it's not controlled by a height. It's controlled by the full length of the catenary. So it's a little more cumbersome to define like the length of the. You don't know exactly where the height of the catenary is going to end up. So it needs a little bit more of background. It's a bit less intuitive, but also at the same time, I will want to mirror this exercise in purely C#, and Rhino Common does not have a catenary implementation, so I will not be able to do the exact same process. Perhaps we can do a geometry gem where we discuss catenaries at some point, maybe in the future, but for the time being, I'm just going to use a simple interpolated curve. Okay, good. So I'm going to group this because I like being very tidy and very clean. So this is the first curve of my span, okay? And I'm going to add this to the group. What is the second thing that I would like to do? I would like to copy this curve and have like a second curve that is moved in this direction by a distance of d, okay, as you see in the diagram. So what I'm going to do is I'm going to create another from d. I'm going to create a vector in the x direction, and I'm going to move this curve. I'm going to move this curve by this x vector so that I have the other curve on the span. And this is going to be a little like this, or this is going to be more like this to look closer to the original building. I don't even know what I'm doing. Okay, and now I have the other curve of my span. Okay, and I can probably start turning off the visualization of these points by I'm hitting Ctrl Q so that I stop the visualization of those points. And the beautiful thing about this is that I can now move this original point anywhere, and you can see how the building is just moving around with me. Okay, what is it going to be next? We're going to draw the curve that is in the middle of the two spans curves. Okay, nice. So I should not be touching my face, right? Okay, I'm sorry. Oh. How are we doing sound-wise? Can you guys let me know if the sound cuts? Because I think my microphone is out of batteries. I bought these microphones. They run on regular batteries. You can't recharge them. I don't like them. And sometimes they crack. They go like, I need to buy something better. But you know, these days buying stuff is not an easy thing to do anymore. Okay. Great. Let's take a look back at the diagram. So to draw the curve that is in between the two spans, I would like to start with the point that I cannot point to, the point at the base, which is going to be a point that is going to be in between the 2 points that form the curves of the span, and it's going to be elevated by a distance of h1. Okay, so that's going to be also fairly easy to do. I'm going to keep using vectors because, you know, I like vectors a lot. So this vector is going to be a vector that is going to have in the x coordinate is going to have a distance of half d, and then in the y coordinate is going to have a distance of h1, which is a parameter here. So I'm going to copy this and I'm going to do half d, and that's going to be the x coordinate, and for the y coordinate is going to have nothing. It's going to be in the same plane, so I'm going to disconnect this. And for c, what we want is h. Okay, so that's going to be, and we're going to take the point, we're going to take the original point here, the base point, and we're going to move it by this vector here. And you can see that it's all the way up there because h1 has a really high value right now, but you can see right now it's right in the middle, okay, of those 2 points. I like that. So that looks good. And then I'm probably going to move this point a distance of w so that we have the other end. And I've done that before, a distance of w, so I'm going to copy paste these two. And because I have this point already, I now have the other point. Okay, so yep, so now I have the other point on the other end. And now I need the third point, which is going to be this one here. Okay, what can I do about this one? What I can do is, if you remember, I have this one here. And what we said is that according to our diagram, what we said is that that point here is going to be on the same plane as these two, but it's going to be elevated at a height of h2. So if we do that, then I can say I'm going to take this point and I'm going to create a vector that is going to be half d, which I already have here, and then so I'm going to create a vector that is going to be half d, which I already have here, and c is going to be h2. h2 is going to have a value of like something very small, and then I'm going to use move, and I'm going to take the point, this point, and I'm going to move this point by this vector that I just created here. Okay, so I have starting point, end point, and middle point. So I think we're pretty good to go. So I'm going to, what am I going to do? I'm going to create an interpolated curve between these 3 points. So this one, this one is going to be the first one, this one is going to be the second one, and this one will be the third one. Okay, and I'm going to turn the visualization off, and this is going to be the curve that is going to define the middle, the center of this span. Okay. All right. So is this parametric enough? Let's see. This is a check that is very useful to do. Let's see if we move the parameters, that do things move around in a way that makes sense. So width, everything is changing accordingly. The height, it looks like things are changing accordingly. The depth, it changes. Things are moving. Nothing is going off. This goes up. This is going up. So it looks like things are pretty tight. So I like what I'm seeing here. So I think we are now at a very good point to move on to the next step, which is going to be which is probably going to be figuring out the ribs. Okay, so let's take a look at that. All right, taking a look at that. So how are we going to do that? We're going to take each one of the curves and we're going to subdivide it in however many points, and then we're going to join those two with straight lines. We're going to join those with straight lines, and then I want to take a look at the situation here where I have the height here, because in the original building the ribs don't start all the way on the beginning. They start like somewhere up here. So I want to take a look at that, and I will probably, what I'll probably do is I will take what am I going to do? What I'll probably do, I'll take the curve and I'll look at the domain, and then I'll reduce the domain a little bit, and I will create a new curve that is going to be just the subdomain of that. Probably something like that. Yes. Oh, let me save this. Yes. Okay. This part is going to be super easy. The only thing that we need to do now in order to create the ribs is to take the starting curve and then the middle curve, divide each one of those curves in the same amount of points, and then just join those points with straight lines, okay? And then for the other end, we can do the same with the two curves, or we can just mirror the initial points, okay? We will have to take a look at this particular situation where of the offset, where the ribs don't start at the very beginning of the curve, but we can take a look at that in a second, okay? So pretty easy. We're going to go to the first curve, and I'm going to subdivide this curve divide curve in a bunch of points. So as I plug this in here, this is by default using 10 as the number of segments, but I probably want to connect this to the parameter that I specified, the number of ribs, which I'm going to set at something a bit more reasonable. Let's say 44, I don't know. Does that sound reasonable to you? Yeah, why not? I like prime numbers a little bit better, but whatever. And then we're going to take, and we're going to copy this for the curve in the middle, in the center, and we're going to subdivide that curve by the same amount of points. Okay, so this is very important because otherwise there's going to be some kind of conflict. Okay, and then very easy now, we can just join these points and these points here, and then create all these ribs. Because we have joined them by the same amount, if we look from the right, you can see that the center, the one in the center, is perfectly vertical, which I believe is how it works also in the original building. Okay, so that's great. However, we have a little bit of a problem, and the problem is that, as we said, I don't want the ribs to start right here at the beginning of this curve. I want some kind of offset so that the ribs start like a little bit farther up. In order to do that, I cannot work exactly with the original curve. What I would like to do is I would like to take that curve and kind of, if you will, kind of shrink it, or maybe take from this curve, take a subset of this curve that starts somewhere a bit higher and somewhere and ends a little higher. Okay, how can I do that? I believe we can do that by creating a new curve from a subdomain of the original curve. What does that mean? It means, if you've seen some of my other tutorials, I just want to remind you that NURBS curves have this thing called the domain. So for example, if I say domain and I pass the curve here, you can see that this is telling me that this curve has a domain that goes from 0 to 12.33. That doesn't mean that the curve is 12 meters long. It means that the curve has an internal distribution of the parameter that goes from 0 to 12 to 12 point something something. And if you want to know more about that, you can check my other lectures. So I think what I would like to do is I would like to find a component that, given a curve, it gives me a new curve from a subdomain of that. So let me look that up and see if I can find something that can do that. Do you guys know of something that I can use to do that? Curve domain, measure and set. Curve to measure, modify, optional domain. So I made the curve. Curve with new domain, domain of original curve. Curvature derivatives, analysis, division, divide, shatter, the curve into segments, parameters to split at. I don't know about that. This sense, I think I saw this the other day, actually. So, closed, curve closed, discontinuity, extremes. Any ideas, folks? Any ideas on how to take like a subcurve of a curve? So if I take this and I say, for example, 1 to 10, this just changes the domain. It doesn't give me a new curve, right? Planar curve, domain of original curve, and then this curve now has a different domain, right? From 1 to 10 as opposed to, yeah. You can do point on curve on both endpoints and recreate a new interpolated curve. Yeah, but that's not clean because like the new interpolated curve may actually not be exactly may actually not that curve may actually not be exactly overlapping the original curve, Albert. So that I don't think that would work. It's not a clean solution, you know. And we're pros here. We want very clean solutions. No, don't worry. It's not your bad. Evaluate curve T. I have a feeling about shatter. Let me check this out. I have a feeling about shatter because if it splits the curve at parameters, and I know that this curve has a domain that is going from 0 to blah blah blah. So if I write here a list where I say 0.5 and whatever 11 point, I would do this programmatically, 11.75, okay, something like this, and I do this, and these are the splitting points. I would get 3 curves, and then if I get the second element on that list, so element 1, so this curve exactly, so you guys see this curve? Do you guys see how the curve starts somewhere here and somewhere here, and somewhere here, but it's the exact same curve. So yeah, so this component is splitting at parameters. So I like that. But then I would like to control the height. I would like to control the height, not the parameters. So what I'm going to do is maybe I can cut the curve with a plane. I can find that cut at which parameter it is. Okay, so let me create an XY plane. XY plane that is going to be moved up by offset distance, which I have not specified. Offset so I'm going to move this up, and this is going to be like a small value, for example. H1 should be a little larger, okay? And then I'm going to do an intersection, a mathematical intersection. So curve and plane, where are you? Curve and plane. So we have the curve, we have this plane, and then it's giving me the parameters on the curve, exactly, which is what I want here, which is boom. Okay, that's what, now we're talking. So I don't want this, I don't want all these division points either, but what I want is the points that are at our control Y and shatter, and this one. And you guys can see how the curve exactly lands here. Now I like that. That I find much cleaner. Yes. So do I have thumbs up? Do you guys approve? Okay, I'm going to redo this, obviously, so that I can explain this a little bit better. Okay, and then I plug this in here, and yes, exactly. Now we're talking. I like this. Okay, so okay. Oh, okay. So where was I? Okay, so how am I going to explain this? Okay, I didn't really find a component that gave me a subset of the curve with a smaller domain, but I found an alternative method, which I'm going to explain right now. And it is due to the fact that what I really, really want to control is the vertical height. Is the vertical height at which this point, so this point here, would start and where the ribs would start. And what I can do is I can divide this original curve, so I can divide this curve, and I can split it at points that I can compute myself. But what I need to know first is what is the parameters, what is the t along this curve that I want to split the curve at. And I think that a good method to do that could be to create a horizontal plane here, then cut this curve, cut the original curve, the first one, along this plane to find the 2 points where the offset is already set and where we would start the ribs. And then if we find the parameter at which that plane cuts the curve, then we can probably split the curve at those parameters and then use the subset of that curve. Let me explain. This is sometimes much harder to explain than to just do it. So let me start by creating a horizontal plane, okay? And I'm going to move this farther down the road. Let me create a horizontal plane that I'm going to move in the Z direction by a factor of offset. So I already created here a variable called offset, and I'm going to move this all the way up. So I'm going to move my plane a little bit vertically, you see? So this is the cutting plane that I'm going to use to trim this curve. And let me turn all of this off. So now I'm going to use a mathematical intersection, and I'm going to compute the intersection between a curve and this plane, the curve being the original curve here, and then the plane, the one that I have just created here. All right, you see, I have now gotten these 2 points on the curve that are at a vertical distance offset from the base plane. And the beauty of this component is that not only does it give me the actual points, but it also gives me the parameters at the curve at which the intersection is happening. So think of this as relative to the domain of the curve. So if you remember, curves have domain, and the domain of the curve here is from 0 to 1233. So you can see that these points are cutting the curve at domain 0, 59, which makes sense, it's like close to the beginning, and 11.74, which also makes sense, which is kind of close to the end. All right, so this is looking great. So I think now I can take a division and I can take a shatter component that is going to take the curve and is going to take the 2 parameters and is going to divide the curve now in 3 segments, in 3 planar curves. This first chunk, the full middle chunk, and the last ending chunk. But since I'm only interested in the one in the middle, I can use a list item component to fetch from this list, to fetch just the second element, which is the one that has index number 1. If I do that, you guys can see that I only have one planar curve, and if I hit here, you can see that highlighted is this curve that is exactly just a subset of the original one trimmed by these 2 points. Some folks in the chat suggested that maybe I could take these 2 points and then the original point on the top and then create an interpolated curve between those three as opposed to this shatter. And that could have been a workaround. It's just that I would not be guaranteed that the interpolated curve would be exactly the same. I believe, I'm not really sure. So I think just for the sake of purity or cleanness or elegance, I think this method is a bit more elegant because it really just gives me the original curve for sure, but a subset, a smaller subset of it. Okay, and then just as I calculated this part here, I can now use this subset of the curve and plug that into the subdivide and create the ribs from this part, from with this offset, which if I make much larger, you can see that it's working great. So I like that a lot. And okay, and then I guess that for the other, so this would be the ribs on one side, and I guess for the ribs on the other side, what I can do is I can just probably, because the domains of the two curves are probably going to be the same, I can probably just take the other curve, no, not this one here, and cut it like that. Okay, and then just copy paste all of this here. So what I've done is for the other curve, I didn't need to compute the intersection anymore, because I'm assuming that since they are clones, the domain is going to be the same, so I can shatter directly on these two parameters and get that subset curve. So I can do now is I can plug that in here, and then I can get the ribs that are on that other side. Okay. All right, this is looking good to me. Let's move the parameters around a little bit to see if things work. This looks like it works. This works. This works. Everything is working. I think everything is very tight and very solid. So I think we're on a good spot to continue with this. So let's move on to the next step. Okay, and with the next step being, what is the next step going to be? We have to do the section of the main beam. So before we replicate this over, I'm just going to create the sections. I'm going to create the lofts I'm going to create the sections, and I'm going to create some pipes here as well. Pipes are really heavy. It's gonna, visualization wise, it's gonna be quite expensive. We'll see. And then we're going to create this section here, and and then the pipes. Yeah. So let's start with the section. And let's start with the section, and for the section, probably I want to mesh pipe. Mesh pipe can be a solution. That is true. Should we draw a diagram for this? We should probably draw a diagram for this. Yes. What am I going to use, by the way? What am I going to use? I'm going to use create a pipe surface with variable radii around a radius curve, base curve, parameters for radii, a list of radii. Nah, this is just pipes. I want to create different sections. So I want to create like a large section here and a thinner section here, but I want the rail to, so I want rail curve, section curves. This is what I want. Yes, this is the rail curve, the section curves, and kink miter type. I have no idea what this is. So I think this is where I want to go. So I'm assuming that if I divide the curve in perpendicular frames, let me do like a quick prototype before I get into recording and messing things up. I'm going to assume that if I do this and then I put some rectangles here, for example, on these planes, right? And I do some sections here. No, this is the curve that I need to pipe in there. I can, yes, and that if I, so I get this, which is probably okay. Mm-hmm. Okay. I think that's what I want to do. Okay, so I'm going to do a diagram. Okay. Okay. Okay, so I'm going to do a diagram. No, I'm going to make this a thinner line. Okay. And I'm going to exaggerate this a lot. Wow, that was bad. Yeah, no, I can't, no. Let's try again. Because then you guys are going to take screenshots of my drawings and then you're going to share them right there and they're going to be like, oh, that guy used to be an architect. Look, thank God he never built anything. Yep. And I'm going to do this. No, this is going to be a new layer. This is going to be a new layer. And then here, this one is going to be, and this one is going to be, this one is going to be. Okay. Okay. And then here I'm going to have a small section. And here I'm going to have a large section. Oh. I'm going to, this is not going to work. Okay. Okay. So this is going to be okay, so these are going to be this is going to be what? D1 and this is going to be D2, for example. Oh, that was a terrible drawing again. Oh God, I don't even know how I get myself into this. Okay, so let's get rolling. Um, I believe the next thing that we're going to do is we're going to implement the, the beams. And for that, I would like to be a little faithful to the original building where we can see that the section of the arch is much larger at the base and is much thinner at the top of the beam. So I have drawn this diagram here, which of course is terrible, but what I would the takeaway of this diagram is that we're going to create a shape that is going to be much wider near the base and is going to be very thin at the very top, and we will want to control the shape of this section in two ways. We will want to have a value for the height of the section at the base, so that's going to be d1. We would like to have a value for the section at the very top, which is that's going to be d2. And then we would like to implement an algorithm that, as we are moving along the arch, the section decreases based on how high up the how high up the I'm gonna say that based on how high up the section is. Okay. Another thing that I would like to probably have here is going to be the width of the section. That's going to be small w. Okay. And so for that, what we're going to do is first we're going to start by doing a section that is constant. So we're going to start with w and d1 for the whole arch, and then we will perform some changes so that the section decreases with the height of the arch. Okay, let's go back to drawing. So where is my mouse? Where is my mouse? Ah, here. Okay, so we have all of this, and that's great. So we have the curve, and this curve is the curve that I want to use. So I'm going to move things a bit here outside of the clutter, okay? And what I would like to do first is I'm going to set some parameters here. I'm going to create them here, and then I will move them back to the origin. So this one is going to be d1, then this is going to be d2, and then this is probably going to be small w, okay? And then I'm going to take this curve and I'm going to subdivide this curve in a bunch of perpendicular frames. So you can see that here I am subdividing in a ton of perpendicular frames. How many? I'm not really sure. I'm not sure how important this is. I think it would be important that the number is even, because we would want one at the very center of the arch. So maybe we choose here to have like a fixed value that is always going to be something like, for example, 30. Or maybe we could plug in a slider here. I don't have a strong opinion here anyway, so I'm just going to leave it there. And I'm going to make the preview of these planes a little smaller so that it's not clogging our view so much. Okay, so now what I'm going to do is I'm going to place on top of these planes, I'm going to draw some rectangles. Those rectangles are going to be defining the section as we move over the arch, then which we will then loft with a surface so that we get a continuous solid geometry. But you can see that all these arches are defined by the x-size in x and y, and they are defined with domains. Okay, so what does that mean? It means that if we want this bottom section here to be of the size w in this direction, we would need to say that the size of the rectangle is a domain that goes from minus half w to positive half w, because we want this section to be centered on the axis of the arch. And then for the height, we would want the height in that direction to be a domain that goes from minus half d1 to plus half d1. So let's implement that. So we have D2, well, not D2, we have D1, and we have the width. So I'm going to create a domain that is going to be, I'm going to create, this is going to be 0.5x, and so that's going to be D, and I'm going to create also something that is going to be minus 0.5x, and I'm going to construct a domain with these two values. Okay, so this, and you can see that my domain now goes from oh, sorry, it's the other way around. From minus to positive. Okay, and if I plug that into the x, then we have this, and then, but if I do the same with w, and I plug that into the y, you can see that now if I hide the planes, and if I hide everything else, I'm going to hide all these bars here, you can see that I have these rectangles that are growing, that are perpendicular to my arch, and that have like a D direction and a width direction, and are going all the way up. Okay, so that is looking good to me, and I think just for the sake of showcasing, I think what I'm going to use here is I'm going to use a sweep one, which is a surface generation method that takes a rail curve. So there's a line, there's a curve that defines the main direction of the surface, and there's a list of section curves that are defining the section of that surface as it moves through the rail. So I think the rail is going to be the curve, and then the sections are going to be all these rectangles that I just created, and you can see that I now have this beam that is the direction of the beam is respecting the axis of the arch, and each one of these rectangles is the section of this beam at that point. So this is looking good to me. But now we need to figure out a way to make the size, so the size of the height of the depth of the section, to be variable according to a height rule. Okay, so let's take a look at that. Okay. Okay, somebody's curve, spline, subcurve. I knew it. I knew it. I knew there was something there. I knew I had seen this point. You're right. Thank you, Kartik. I knew I had seen this component somewhere, but whatever. Maybe I can talk about it later. But anyway, I think this was helpful as something interesting as well. I don't know. Honestly, this would have worked but it would only work to replace shader and list item, because we still need to do this process of cutting the curve with the plane if we want to control the height of the offset by a z distance. Yeah, but that was a good call. Thank you. Okay, going back to the planes. How am I going to explain this? I'm going to explain this by specifying that I need to make a rule where I compute how far off each one of these points is from the point in the bottom, and then we subtract that difference from the height. Okay, let me explain that. And how am I going to do that? I got it. Okay, great. The way we're going to do this is by implementing a very, very simple numerical rule where we have two sections here. One has a height of D1, the other one is height D2. And what we need is, based on how high or how far from the ground each one of the sections is, we need to reduce incrementally between D1 and D2. Okay, I'm actually going to do this example with numbers. So let's say I'm going to create a new layer here. I'm going to draw some numbers here. Let's imagine that the section that we have here is, for example, 75 centimeters. And the section that we have here is 50 centimeters. And we have 1, 2, 3, 4, and 5 sections in the middle. Okay? It's kind of easy to see that this one should have 70, this one should be 65, this one should be 60, this one should be 55, and the other one should be 50. Okay? But how can we find a numerical rule to do that? Well, if we know that the difference between these two sections is 25, so 75 minus 50, if we know that the difference in the depth of the section is 25, what we can do is we can compute a rule where we say how far off from 0 to 1 is this point from the base. So if this is 1, we can say that, because it's 5, we can say that this point is 0.20 away from the bottom. This one is 0.40 from the bottom. This one is 0.6, 0.8, and this one, the top, is a full 1.0 away. This is called a normalized distance. We're not measuring the real distance, we're measuring the proportional distance between the two ends. And then if we take and we multiply the proportional distance by the actual difference in those two sections, so this 25 multiplied by 0.2 gives us 5, so we can subtract 75 minus 5 is 70. If we multiply 25 times 0.4 is going to give us 10, so 75 minus 10 is going to give us 65. And then, so basically, if we multiply the normalized distance by the difference that we want between the two sections, that's going to give us how much do we need to subtract from the main section height to get the proportional section height at that interval. Was that clear? I'm not sure about this. Sometimes I see these things clearly, but I don't know if I explain this in a way that makes sense. Let me show the implementation, and then we can judge. So we have the base at the point at the base, which was this one here. Okay, so I'm going to take this point at the base. I'm going to bring it all the way to where I'm working, and I'm going to take the other point that was, what was it? It was the point at the top. It was this one. So I'm going to take that point at the top here. Those are the 2 points, my 2 reference points. Okay? Point on the bottom, point on the top. This one I'm going to deconstruct so that I can find the z property of each one of them. Okay? And so that I can find this z property of each one of them. And actually, I don't really need the one in the top. Sorry. Now, I have D1 and D2. I can subtract one from the other. So D1 is going to be bigger than D2. So D1 minus D2, this gives me the difference in section depth. Okay? And now what I can do is I have all these frames that I have created, all those planes, each one of those has an origin point. So if I can deconstruct the plane into each one of its components, you see that it gives me a lot of points, and that it gives me the x, y, z vectors of those points. So if I deconstruct the origin, I can see that here I can get the z coordinate. I can get the z coordinate of each one of those points. All right. Okay. And if I now subtract the height of each one of those points minus the height of the base point, you can see that this is how far off each one of these points is vertically from the one in the bottom. But this is the Euclidean distance. What I want is a proportion. I want to know if these points are from a scale from 0 to 1, how far off each one of them is. Okay, and and for this, for example, I can take the maximum of all these points, or no, I can actually take the point that I deleted. I take this point here. I take, where is this point? No, not this one. I take this point here. Yes, I'm going to bring that point, the point on the top. I'm going to find its height. Okay. And then I'm going to divide each one of these heights by the height of this point. And you can see that now what I get is a nice list of relative heights. So this point is proportionally is like 0 distance from the base. This one is 0 point something, 0 point something, and it goes increasing all the way until 1, which is the point at the top. The point at the top proportionally is the farthest away in the vertical z height from here. Now, I know what the large section is, so this is D1. I know what the smaller one is. I know what their difference is. So if I multiply this proportionally, the proportion from 0 to 1, with the difference in sections, you can see that I get a list of how much do I have to subtract from each one of the sections. So from the section in the base, I have to subtract absolutely nothing. And then I have to start subtracting a bit more, all the way to the center, in which I have to subtract the full 0.48. Let me make this a bit more round numbers. So if the section at the base is 70 and the one at the top is 20, you can see the difference is 0.5. And you can see that now I have created a list of how much the section gets reduced as it goes up on the arch. So now it's just as easy as saying for each one of these sections, so take D and now subtract from D, from the value of D, each one of these increasingly diminishing sections, and then plug this value to where we are calculating the heights of the section. You see that? And then you can see that now each one of the rectangles has a different depth, and that depth is proportional to how far off they are from the bottom. Okay? This was a little convoluted to explain. I hope I did a good job at that. But let's see if this actually works. So if I if I change the base, you see that now it's much thinner. Now it's very thick. This is actually quite cool, actually. Very thick. This one increases. Now it's very, very thin. Okay, the width is constant. That doesn't change. Okay, and then if I mess up with the height of the whole thing, you can see that we still get the nice proportional effect, because everything is parametric. It doesn't really matter how high this is in Euclidean space. What matters is the difference between this point and this point, and that is how things are computed here then. Okay, that was cool. Let me shrink this a little bit. I don't like it's looking too fat. It's looking too wide, and this okay, I like this a little better. Okay, and so this was for that one, and I'm going to group things a little bit here to make things cleaner, and I'm going to leave this here because I will want to move it at the beginning, where all my parameters are. And I think we can probably apply this to maybe this. We can apply the same logic to the curve in the middle, or maybe we should use two other different parameters. I'm not sure. So I'm just going to do a different one because yeah. So I'm going to copy all of this and paste it here. I'm going to give this different names. So this is going to be the one in the middle. This is going to be the one in the middle. This is going to be the one in the middle. Okay, and I'm going to reduce this. So that's going to be 0.6. This is going to be 0.1, and this is going to be because this is not really carrying much stresses. But the curve that I'm going to plug in here is going to be the one in the middle. The one in the middle, but the points that I need to plug in are different. This has to be the point at the base, which point was that? It was this point here, and for this one, this was the middle point, so that was going to be, that's going to be this one. But we could have actually done this a bit more programmatic, and instead of relying in the previous points, we could have just take the start point of the curve and the middle point of the curve, and make things a bit cleaner. But yeah. Okay, so I'm gonna clean this up a little bit, and okay, and so now it looks like we have the profile curves. Okay, so what is our next step? Okay, what is our next step? I guess our next step is just going to be, we have everything, right? So we have the axes, we have the surfaces. For the beams, we have everything. I think the only thing we just need is like to replicate this infinitely along D. So let's do that. Okay. What do we want to do? And I guess the last thing that we want to do is we have everything ready to go. So we have our ribs, we have our our beams. We have the surface for the beams. We could put some pipes here. So we could put some thin pipes here, curve, and the radius is going to be something like something small probably. So that's going to be, the radius is going to be something like 0.01 or 0.03, oh, 0.03, you know. So we can probably just put some pipes in here. Pipe radius. And I guess the only thing that's left is like to take all this geometry and then to replicate it in a matrix going in this direction. So that's going to be super easy to do. So let's take a look at how to do that. I'm going to create the number of spans, okay, and we have these spans. So what I'm going to do is I'm going to create a series of numbers, and I'm going to create a series of vectors with those numbers, which are going to define how many repetitions we do. So I'm going to create a series, and I'm going to the first number is going to be 0. Like the number of the step size of each successive is going to be 1, and the number is going to be, so here let's say I have 10 spans. So here you can see that we have this many elements, and I probably want the step size to be d, so that what I'm going to create is vectors that move this geometry 1.5, 3, 4.5, 6, etc. in the x direction. So I'm going to create a lot of these. I'm going to create numbers they increase successively, and then I'm going to use a x vector to create translation vectors. And now with this vector, I can just very easily start taking geometry that I want to replicate and start moving it with all these vectors, creating a matrix. So for example, what is the curve that I want to take? What is the curve that I want to, so this curve. So this is going to be, for example, if I bring this curve, this is the main curve. I want to replicate it like 10 times, for example. Okay, so that's going to be the main curve. Something that I want to replicate 10 times as well is going to be the middle curve, the one in the middle. So for example, where is the one in the middle? The one in the middle is it this one? No, it's this one here. So I'm going to take this, I'm going to plug it in here, and then I'm also going to replicate this 10 times. So we have that. Now I can also bring in all my ribs. So for example, the ribs are, the ribs are here, I think. These are the ribs. And yeah, okay, and I'm going to need to do some modifications there. And those are the ribs, yes. And you can see that the ribs are doing something weird, and that something weird is happening because of data, okay? So you can see that, no, where are the ribs coming in? Yeah, so these are the ribs, and you can see that I have a list with a bunch of elements, but I also, for the translation vectors, I also have a list that has a bunch of elements. So what's happening is that the first one is being moved by the first vector, the second one is being moved by the second vector, the third one by the third vector, the fourth by the fourth vector, and that's why you see the first one here, the second one here, the third one, and one at a time until the very end, which uses the last vector to repeat that. This has a very easy solution, which is to graft the tree, and then to just use the grafted tree there. If you want to know more about why this is the case, you can check my intro to Grasshopper series, and where we do data manipulation. And now here we have all the ribs. There you go. And I can also do a similar operation for the B reps. So where are the B reps? So here are this guy here. which is going to become all the way down, and then probably this one I want to replicate it as well, and probably I want to graph this. Okay, and then I can do this with the pipes probably as well. Where are the pipes? Yes. So pipes and pipes. Okay, and then I have everything replicated except that the very last arch is missing. And that's because for the last one, I probably want to use a series where I increase this by 1 unit. So I'm going to keep this for everybody except for the first one. So I'm going to here, I'm going to copy in this, but here in how many elements I want, I'm going to create an expression. I don't like creating expressions in components. I like to have this, so maybe I'm just going to replace this here and then create an expression where I say this is going to be x plus 1, and so I'm going to increase by 1 value, and then so that creates a list of vectors that is 1 unit longer, and then that's the one that I'm going to use so that I have an extra element at the very end, and I'm going to use that one also for the vrep that is coming from here, so this one. So I'm going to copy and paste this, and I'm going to, and this I'm going to disconnect this one, and for this one I am going to use this other list, the one that has an extra element at the very end. Okay, and I think with that we are in. I'm going to group everything that is curves in one component here so that I can turn them on and off with one go, and I'm going to group everything that are vreps here with one component as well, so that I can see, I can turn everything on and off just with one component. And I'm going to disable the visualization of everything in the middle, and piece of cake. So now I can turn everything on and off. So you can see that I can only show the vreps. So I have my very nice building, and I can mess around now with the widths, and I can mess with the heights, and I can mess with the number of ribs, and I don't know. And if I want the surface, because I want to render it for a competition, then I already have this. This is the geometry that I can bake, for example. So I can bake this. But if I don't need this, this is very expensive to compute. So what I can do is I can disable this component so that the whole definition is a bit more lightweight. And what if I want, there you go. And here I still have the curves, which are useful for me to generate, for example, like the axis diagrams or the structural plans would be very helpful to just have the axis lines as opposed to the vreps. Okay, so so I think with this we're pretty good to go. I hope this was useful, and stay tuned for more algorithmic modeling challenges. Thank you. Okay, how was that? Okay, I need to record the introduction, right? I need to record the introduction, yes. So I'm going to move all of these parameters. All these parameters here. And you see how we almost did nothing and we already have a huge spaghetti of stuff here. This is classic Grasshopper life. Okay. Was that intense, Sujay? I thought it was, yeah. Okay. Oh, and I forgot to mention, I'm probably making a second part of this video where I'm replicating this whole thing, but with C# components. So with a full C# component. So stay tuned if you wanna see more. Maybe like there's like a link showing up somewhere, etc., etc. So stay tuned if you wanna learn how to do this in pure C# scripting. All right. Yes, I forgot to say that. Okay. Now, how am I going to record the introduction? I'm going to probably start with this. I'm going to probably start with this, just as is. And am I going to start with this? I'm going to start with it. Am I going to move this around? And I'm going to, what am I going to do? Am I going to move this around and show the definition working? I may want to do that. Yeah, why not? And I'm going to show the building. Yes. Okay. Is this a nice angle? Okay. Hi, and welcome to another algorithmic modeling challenge where we're going to model Calatrava's Liumbraco, a building that it's in the City of the Arts in Valencia. So it's this thing that has like a garden underneath, and it's like a walkway in front of the City of the Arts in Valencia. And what you're going to see is that this is going to be a really nice exercise on basic geometry, form finding, and a little bit of data manipulation, data list, a little bit of data manipulation. So I'm going to show you. Okay, I'm starting over again. This was not good, not good, not good. I don't. Maybe I should just not. Maybe I should just not show this working or show this. Yeah, I don't want to manipulate the sliders. It's fine. Westworld? Oh, you're right. This is on season 3 of Westworld. You're right. Uh-huh. Okay, I'm gonna say that. Thank you, Rafael. Okay. You're right. You're right. Somebody told me before. I haven't seen. I've seen season 1 and 2. Season 2 was terrible, honestly. You guys, are we gonna talk about that? We can talk about that in a second. But season 2 was. I found it so bad that I basically have no desire to see to watch season 3. But we can talk about that later. Okay, let me repeat the intro video. Hi, and welcome to another algorithmic modeling challenge where we're going to model this structure that you see here, which is called the Umbraco, and it's a building by Calatrava on top of the city of the arts and the sciences in Barcelona. I was just informed by people on the chat that this building was on season 3 of Westworld, the TV show, which I haven't watched yet. I stopped at season 2 for multiple reasons. So, but it's going to be an interesting exercise to look at this building, just because we're going to implement like a lot of like very basic form generation. We're going to do some special manipulation of curves and subdivisions of curves, and a little bit of data tree manipulations and list manipulations as well. So it's going to be an interesting challenge, I think. We're going to end up with quite some spaghetti, but I hope it's going to be just tedious but not complicated to understand. Okay, so let's get to it. All right. All right, so up. Ooh. Okay, so we're good. I think I need a rest. I need some real world. I was not recording. I was not recording. Oh my god. I forgot to press record. Oh no. Well, we'll just take the video from YouTube, I guess. There's nothing we can do about that. Oh, that sucks, man. Ah, no. Rami, are you there? Oh, this sucks, man. I'm sorry. Uh, well, what can we do about this? It's gone. So nah, we'll just download the video from YouTube and edit that video and whatever. If it has less quality, then be it. Well, we can't really do much more about that. Anyhow, um, okay, so I think I'm done with this. Um, Man, I'm so angry about that. How did I forget to record? Ah, you see, I was very tired when we started this. Anyway, my fault. I should have paid more attention. Okay. All right. I can probably do some Q&A if you guys are up for it. Um, otherwise, otherwise, we can probably take off and start the weekend, which is looking super sunny and nice here. So, so let me take a quick break. I'll be right back. If you have any questions, start posting them here and we can talk about those. I'll do 5 minutes of Q&A and then we can take off, okay? Okay, I am back. Okay, are we gonna talk about how terrible Westworld Season 2 was? Because I did love Season 1 and I was very disappointed about Season 2, honestly. Also, I could open a beer and we could start the weekend together. Oh, how awesome would that be? Huh? Or like a cold white wine. Today is very nice weather out here. Okay, any questions? Alka has weekend vibes. I do as well. Uh, okay, was there any question up in the? Oh, I forgot to mention about the subdivide curve there on the recording. Uh, it's okay. I mean, the process was going to be very similar anyway. Um, do I have record? I have saved this. I have saved this. Yeah. Uh, Man, that sucks. I feel so bad about that. About not recording the. I mean, it's okay. It's everything is on YouTube anyway. Can we define the catenary curve using an expression? You can, and actually the equation of a catenary curves is fairly straightforward. I think it's a I forget, but the literature is out there. I think it's like hyperbolic cosine or something like that. Um, but but the thing is, the algorithm to find the equation of a catenary curve given 3 points is actually not very straightforward. So if you have the equation, um, generating all the points of a catenary is very easy, but the equation doesn't really give you the points that is going to nah. So it's very difficult. It's not very difficult. It's tedious. It needs some development to generate the equation with the constants that you need, the equation of the catenary given 3 points, which is kind of what we needed here. Even just having 2 points and the length of the catenary is also not straightforward to do. So it just requires a bit more of computational geometry, but again, maybe that's something that we can do as a geometry gem. I would have to do some research beforehand, but yeah, it would be an interesting exercise to do, nevertheless. Next Saturday, C sharp. Actually, okay, so maybe what we can do next Saturday is to do this exercise that I just did in C sharp, so in a C sharp script component. But I do really want to start like the basic intro to Grasshopper, series. So maybe if I do a 2-part recording, a morning and afternoon, we can do this exercise, C sharp scripting, and then I can start the series in the afternoon or in the morning or whatever. I don't know. I think Rafael doesn't want to address Westworld. He went totally silent. Somebody told me also that in season 3, there's like they feature the Atlas Cafe in Singapore, which is a place that I was at like a year ago. My friend Zach, who's been on the chat a couple times, took me there. It's such a beautiful place, but I haven't seen the episode yet. Maybe do an algorithmic challenge on Gaudi for catenaries. Yep, that could be super interesting. That could also be super interesting. Oh, look what Alka said. Rafael. I totally agree with you, Alka. Well, I don't know. I haven't seen season 3, but I didn't like season 2. I was very disappointed. Also, I don't have HBO right now, so I don't know how to watch that. Honestly, it's okay, Rafael. We're all entitled to our own opinions. It's perfectly fine. Okay. Okay, so before we start picking up a fight about random TV shows, I think I'm gonna call this a day. Oh, season 3 is even worse than season 2. Oh my god. Okay, I don't want to know about that. So before we start picking up a fight about which is the worst Westworld season, I think I'm gonna call it here. I would like to thank everyone for staying all day around. I hope this is helpful, and I hope this helps push your computational design skills further. And stay tuned, subscribe, join the Discord, etc. And stay tuned for. Remember, we're going to be doing Saturdays for the rest of the semester, for the rest of the summer. Okay, so I'll see you guys next Saturday next week. Okay, thank you very much. Thanks everyone. Bye.